Today, we will introduce our work on the unknown object detection called Unknown Sniffer. This is a joint work from Liang Wenteng, Xue Feng, Liu Yihao, Zhong Guofeng, and Ming-An Long. In the fields of autonomous driving and robotics, deep learning-based perception methods have achieved outstanding performance, such as semantic segmentation and object detection. However, many of them rely on the closed word assumption, which limits their ability to identify never-seen-before objects. Therefore, it is necessary for the model not only to detect objects within predefined categories, but also to identify unknown objects. In recent years, several algorithms for detecting unknown objects have emerged, including open-set detection and open-world object detection. Open-set detection aims to separate known and unknown objects. It simultaneously suppresses the unlabeled unknown objects and non-objects hidden in the background during training, which results in many unknown objects being treated as non-objects during inference. On the other hand, open-world object detection requires not only distinguishing between known and unknown objects, but also involves incremental learning in the detection model. However, existing algorithms such as ORE and OWDTR extract pseudo-unknown objects as negative samples. We found that these pseudo-samples cannot represent unknown objects well, which limits their ability to transfer knowledge from known object to unknown category. In summary, the existing algorithms lack the ability to clearly distinguish between known objects, unknown objects, and non-objects. To solve these problems, we propose the unknown sniffer, which mainly has three contributions: generalized object confidence, negative energy suppression, and graph-based bounding box determination strategy. To start, we designed a generalized object confidence score with two motivations. Firstly, we found that the deep features extracted by the backbone network actually encode many unlabeled objects. Secondly, unknown category has a large overlap with known categories in the feature space. This means that many known objects share common features with unknown. So we hope that our network can recognize unknown objects based on the features learned from known categories. For example, if the training set includes cat and dog, we hope that the network can learn the common features of cats and dogs to recognize deer as well. To achieve our goals, we divided the training samples into complete object, partial object, oversized, and non-object boxes. During training, we exclude the non-object boxes to ensure that the model doesn't suppress unknown objects. Next, we designed three different loss functions. The first one encourages the network to output a score close to 1 for the complete object box. The second one compares the scores of each two bounding boxes and push the network to give a higher score to the complete object box than the others. Finally, the third one suppresses the scores of oversized and partial objects. They are used to train a new branch that works alongside the classification and regression heads. As we can see, using the above supervision greatly reduces the score of non-objects, indicated by the green line, and significantly improves the scores of known and unknown objects. This proves that Our unknown sniffer is effective in distinguishing unknown objects and non-objects, which is crucial for real-world applications. The GOC branch assigns a high score to both known and unknown, but due to the lack of unknown annotation, we end up with lots of bounding boxes with high GOC scores around the object. In this case, if we use non-maximum suppression as post-processing, it might accidentally ignore some unknown objects. Because we don't know how many unknown objects there are in the image beforehand. To find the best bounding box, we create a graph with all high GOC boxes and use graph partitioning algorithms to group them into clusters based on their IOU. Then we choose the highest scoring bounding box from each cluster as the final box for that object. In our network, we use the energy loss of VOS to separate known and unknown. However, non-object proposals may receive high negative energy scores due to the insufficient data, causing similar energy score between non-object and object. So, how can we further distinguish them without non-object annotations? We noticed that bounding boxes with the lowest negative energy scores are usually non-objects. Therefore, we decided to sample the top T bounding boxes with the lowest negative energy scores and further reduce their energy. It helps to make the difference between non-objects and objects even clearer. As you can see in the image, the overlap between the green and yellow lines is reduced even further. Finally, this loss function is combined with the VOS energy loss as the energy supervision. To assess a model's ability to detect unknown objects, we designed a benchmark. Our benchmark leverages the Pascal VOC dataset with 20 object classes as the training set, which is the same as VOS. For detecting known objects, we utilize the VOC test set. For detecting unknown objects, we sampled over 1,400 images with clear object regions from COCO dataset and relabeled them with instance-level annotations to form two datasets. The COCO-OD dataset only contains the unknown object. In contrast, the COCO-MIX dataset contains both known and unknown objects and can be used to evaluate the confusion between them. Our evaluation metrics are mainly as follows. Before the evaluation, we implemented a pretest mode that utilized 200 images from VOC dataset to determine the parameters of our network without leaking the test set. The results showed that UN Sniffer achieves the best performance in UAP and UF1, although there was a 2% decrease in performance for known object detection. We can still ensure a high accuracy and recall rate for unknown. In addition, the ablation study further verified the effectiveness of each individual contributions. Next, we will give some visualization. As you can see in the figure, our approach doesn't generate a ton of boxes, but it can still effectively detect objects that do not exist in the training set. Previous methods either generated a bunch of false positives or failed to detect enough unknown objects. Since the space of the main text is limited, we provide more visualization results in the supplementary material to demonstrate the effectiveness of our methods. From the demo video of the real scene, we can see that our algorithm greatly reduced false positives when compared with ORE and OWDTR. Moreover, in the comparison to VOS, our algorithm more effectively detects unknown objects. In the street scene above, the results presented in the video demo are consistent with the previous conclusion. In addition, we also tested our algorithm on the lost and found dataset for road obstacle detection. That's all. Thanks for listening.